do have a lot to go through today. I'm not sure we'll be able to go through them and do the worksheet. We'll see how the timing comes out. Maybe we'll just get started on the worksheet. But just a reminder that on Monday, right, which is going to be the next time I see you guys, right, there's the midterm. And there is the midterm review discussion that I think only one person posted on it so far. It is 10 points, so it's a free 10 points, right? Just by posting, oh, this problem I was kind of, is interesting or it's confusing, or, oh, I just didn't get, like any homework you miss, right? Just post it on there, right? You get to pick one problem per chapter, and then I'll make a little lecture videos for it on Friday, and therefore you guys can use that to study for the final over the weekend. Okay? All right. Any questions or concern about the midterm? Right. All right. Hopefully we're going to get through the rest of this chapter today. Okay. So far we did double slit, many slit, which is the diffraction grading. Now we're going to also do one for single slit. So what happened is that even if you only have a single slit, you still get these diffraction, this interference pattern. So so the pattern that you see here, but it is a little bit different from before, right? Remember the double slit one, right? You always have, if this was a double slit one, okay, the double slit, right? These stripes will be evenly spaced apart, right? Where the diffraction grading, double diffraction grading, right? There you have one strong central one, and then as you go away from it, they get further and further apart, right? And then single slit, okay? The thing we're going to focus on is actually basically the width of the central maximum, okay? How wide is this? So you get a much wider central maximum, and then the rest are kind of like, the width kind of goes down and down and down as you go further away. So the way you make a single slit diffraction pattern is the same thing as you would do a double slit instead of two slits, right? You pass the light through a single slit, and then you actually see this on the other side. And we're going to figure out also, well, how wide does this slit have to be in order for us to see this, okay? In order for us to, we're not going to really derive it, but it's kind of in principle, think about it, right? This is going to be what's known as Huygens principle, and probably saying his or her name wrong, right? It's probably some Dutch name, where when light passes through, or just actually any wave, doesn't even have to be light, okay, passes through a single point, you can treat each of points on the wave front. So pretend you have a wave traveling this way, right? Each of these points here can be treated as a point source, okay? And what happened is that as these wavelets, they call wavelets, propagates out, they will either constructive or destructively interfere with each other, and therefore you produce an interference pattern, even though you only have originally one single light source, but then you're treating each of these, the line along this wavefront, as if there are multiple wave sources, okay? Similar thing happen if you have spherical waves, right, where you just throw a little rock into the lake, right? What happens is that each of these points become their own kind of source of waves, okay? If we apply Huygens principle, and then what happens is that you see something that's similar to the diffraction grading situation, right? Where you have a single slit, right, that has some width A, right, with A, okay? And as the wavefront passes through, let's do that in red, okay? Passes through here, instead of just a single wave, you create a bunch of tiny little wavelets, right? As these little tiny wavelets comes out, if the crests matches up with each other, like these, right, then you have constructive interference. That's where you see the bright spots, right? Okay, where the crest and the trough matches up with each other, then you get destructive interference, right? And therefore you get this, bright, dark, bright, dark, bright, dark pattern once again, okay? If we try to do this analysis, let's say we just start off with just some reasonable amount of wavelets as opposed to infinite. Let's just start off with 6, okay? You got 1, 2, 3, 4, 5, 6. We're just pretending a plane wave is coming through, okay? And we're treating each of these little dots here as if they're sources of circular waves, right? So these waves are going outward like this, okay? And basically the pointing vector for these things, right? The direction the wave actually goes, right? Let's say you're at a screen some distance away from this, right? And you want to figure out whether or not you're going to have constructive or destructive interference. Once again, the variable that we want to figure out is this delta r, right? If delta r is some integer multiples of the wavelength, right? 2, 3, right? Then you have constructive interference, right? The delta r is a half integer difference, right? Then you have destructive interference, right? Hopefully this is kind of like the same no matter which system you're dealing with. So it's nice to just actually know that. That's the most important thing. What is the difference in the distance that the light has to travel, right? And that's the delta r, right? So this light has to travel a little bit further, and this beam has to travel a little bit further, this beam even further, right? And that's the delta r we're dealing with. Okay. We're not going to go through the math in too much detail in this case because we kind of went through it multiple times already with the double slit and the diffraction grating. What ends up happening is that your delta R turns out to be basically going to be whatever the wavelength of that light is divided by 2, okay, right? And then in general, what you can do is you can find all the dark fringes located at if p is some integer, so I don't know why the book decided to use p instead of m, okay? If p is some integer, 1, 2, 3, okay, then if this equation is satisfied, then you would actually find the dark fringes of the single slit interference pattern. What we're actually going to focus on is basically figure out how big is this central peak, right? So this is very different from the other interference pattern we had before, where the central peak, go up here, is much wider. Ooh, that's a bad color to draw over red, right? Red over red. Come on, do the green, right? We're trying to figure out what this width is, okay? And that's going to allow us to actually measure basically like, you know, the wavelengths or even the distance that the source is actually creating this interference pattern. Okay, so to derive this central peak, first of all we have to figure out how much of an opening angle that has, right? Right. Once you have that opening angle, and then you know the distance it travels, you know exactly how wide that peak is. Okay, right. So this angle here, right? If we follow this equation and we do a little approximation where, you know, theta p is approximately sine of theta p once again, right? We're doing small angle approximation once again. We're going to have this condition where, right, the angle of opening that's coming out, right, of the single slit, right, theta p, is going to be equal to whichever the p is, right, some integer that starts with 1, 2, or 3, right? So this is going to be p equals to 1. Down here is p equals to 1. The one right in the middle is actually p equals to 0, right? Right? And that's going to be equal to the wavelength divided by basically the width of the single slit. Okay? Right? So what happens is that you're going to see patterns like this. Okay, I could have just scrolled down. Okay? Okay? Where, for example, for p equals to 1, right, this will give you theta 1. Okay? And this theta 1 is going to obey this equation here where, well, for p equals to 1, that's just going to be a 1, the wavelength divided by the width of the slit. Okay? Pretty simple. Okay? So once again, what we can do is that, well, if we want to figure out this width here, right, this width is going to be, over here is the width divided by 2, right? Because we have half the width on the top, half the width on the bottom. Okay? Right? So if we know the angle theta here, right, tangent of theta 1 is going to be W over 2, right, divided by basically this length here, which is L. Okay? And once again, what we're going to do, we're doing the small angle approximation. If L is much bigger than A, right, then theta is a small angle, and therefore theta is going to be approximately, um, sorry, side tangent of theta is approximately theta, right? So we have this condition here, right? And then previously, up here, right, we have this relationship where theta is actually the wavelength divided by A. So now we have this relationship between the width, um, the distance to the screen, the wavelength, and the width of the slit, right? So what you can do is just solve this equation for W. We solve this equation for W, the 2 goes on top, the L goes on top, and the A goes on the bottom. Okay, so that's how wide that central peak is going to be. Okay, okay. And if you see this with different color lights, okay, the bluer light is going to give you a narrower peak, right? Right. Sorry, narrower band in the middle because, right, the smaller the wavelength, the narrower that width going to be, right? The longer the wavelength, the more spread out that central band's going to be. Okay. Right. So with blue light, it's going to be narrower. With red light, it's going to be wider. Okay. I'm going to skip most of these equations because we just derived them. Unfortunately, I just kind of did it all just by writing. Okay. And that's basically the important thing you want to remember from this section, where if you want to figure out the width of a single slit interference pattern, right, you calculate it with this, right? Usually what ends up happening is that you actually can measure the width, right? And then you actually can figure out, either, the width of the slit or the wavelength of the light or something like that, okay? Because the measuring this is easy, where if you're trying to measure the width of a tiny, tiny slit, right, that's going to be very difficult, right? Okay. There's this question here, just for the sake of time today. I'll just go through it as an example, right? So let's say we have the following picture here, right? And there are two slits, one with A1, one with A2, okay? Are we able to tell the relationship between A1 and A2? Which slit is wider, okay? So what we do is we write this little equation down here, right? This is 2 lambda L over A, right? So that means, right, A2 has a broader, right, width, right? It has a bigger width, right? So if the width is is increasing, right, the A has to be smaller, right? Because they're inversely proportional to each other, right? Everybody this is too easy now, right? Okay. All right. Therefore, we know that, well, A2 is, well, so W2, ooh, which is actually close to my acronym, my email address, right? W2, right? W2 is bigger than W1, so we actually have to know that, well, since they're inversely proportional to each other, therefore A2 has to be smaller than A1, right? Okay, hopefully that makes sense. Okay. And then if you actually want you can actually measure the value if you know the wavelength and the distance to the screen. You can actually calculate exactly what this is, right? Because you have 4 variables. If you know the other 3, you can calculate the 4th one. Okay. Right. So that's the single slit diffraction interference pattern. Okay. What we're going to do is we're going to jump. Notice that we started this previous section was 33.4. We're going to jump to 33.7 and just discuss, when we have these interference pattern, right? How do we determine whether or not we should be treating light as a wave or a ray, right? Okay. So in the single slit, let's not do that, okay? Because I actually kind of skipped that equation. Okay. Let's look at this picture here, okay, where we have a single slit, right? And the waves are coming out of the single slit, right? And let's say, this one particular wavelength, right, has, some opening of theta 1, okay? Another wavelength, right, happens to have a much wider opening, right? So this theta is actually P lambda over A, right? Okay. So this wavelength is actually much bigger, right? How do we determine whether or not that the wave behavior here is actually important or not? Okay. So for a very short wavelength, okay, you're going to have a very narrow beam that's coming out. But for bigger wavelength, okay, you're going to have a much wider beam that's coming out, right? A much wider pattern that comes out, let's say, okay? Right? So the rule is that if the spreading due to diffraction is less than the size of the opening, then what we're going to use is we're going to use the ray model of light, which is what we're going to talk about next chapter, okay? But if it's the other way, right, where the spreading is greater than the size of the opening, meaning how much this spread, right, this W here, right, is bigger, oh, sorry, yeah, it's bigger than whatever A is, then we have to use the wave model of light, okay? So this is sort of like, it's kind of like a rule of thumb more than, you know, than actual like, oh, there's physics behind it. Because, right, if you have a very, let's say you have a beam of light, you know, we can draw like a maybe purple light, right, and it comes out straight like this, basically, right, right. Basically, this you can treat as a beam, right, where the counterexample where you have this very wide wave that's coming out, right, you should treat that as a wave, right, as opposed to a beam, okay. And both of these pass through the same opening, right? It's just the wavelength of the light that happens to pass through is different. Therefore, you either get more spread or very little spread, right? What we're going to do is we're going to try to do some quantify this with a quick example. And the example we're going to use, actually the book uses, is actually the ones from the circular aperture. It's very similar to what we just calculated. Instead of the width being twice the wavelength times L over the space opening, right, it's just 2.44, okay? It's just a slightly different equation, okay? So what we need to do is figure out, well, this width of the beam that's coming out, right, this is W, right? Right? Instead of A in a circular aperture, you use the letter D instead, okay, for diameter, right? So that's the same thing. So treat D as just like A, okay, right? What we want to do is we want to impose this condition where, right, we want to figure out whether or not the diffraction width, right, is comparable to the size of the opening, right? Okay. So the diffraction width is over here on the left-hand side. The opening, right, is on the right-hand side here, right? So if we want to compare them, right, what we can do is just set W to be equal to what's going to be some the variable DC that the book is using. This is the critical diameter. Okay, we're going to call this the critical diameter. Okay. So if we make that equals to the critical diameter, we make this equal to the critical diameter here, right? We end up with two factors of this, okay? Solving this equation for DC, you end up with basically approximately square root of 2 lambda times L, okay? I know this is 2.44, but we're just gonna have an approximation there, okay? So if we were dealing with green light, for example, green light has a wavelength of about 500 nanometers, okay? We plug the wavelength of the light here, and let's say we're dealing with a screen that's about a meter away. We plug in L there, okay? And we just, you know, punch this into a calculator. We get a critical diameter of about a millimeter, okay? So, right? Oh, these are, yeah. So one of the finest um, increments on a meter stick, okay? So that means, right, if the slit, right, is smaller than a millimeter, we have to treat that light as waves. But if that slit is bigger than a millimeter, then we can actually treat it as a ray. Okay, so that's what we're going to be determining. Okay, right? So let's do an example. Any questions about this before? There's this, I think this discussion is kind of useful because sometimes you use ray, sometimes you use wave, and depending on which experiment you're doing, like people just arbitrarily picks it. But there is a reason why, and this is sort of what we're trying to discuss. Okay. Any questions? Okay. So this condition, right, is actually what you want to impose if you want to determine whether or not something should be a particular system should be treated as a wave, right? Right. If this um, if DC is less than this quantity you can calculate, right, you should treat it as a wave. If it's greater, then you should treat it as a ray, which is what we're going to do next chapter. Okay. All right. I'm going to do another example, right? That's a little bit different. We're going to deal with it in terms of sound wave. Sound wave is also the same way. Okay. So wavelength of sound, you can calculate it from just the speed of, right? For any wave, actually, right? The speed of the wave is actually the wavelength times the frequency. Okay. Let's say we have, this is frequency, right? Right. Let's say we have a sound that has a frequency of 1 kilohertz. So it's kind of like a high-pitched sound, right? Little, right? I'm not going to try to make that again. Okay. What? Repeat what? No, I can't. Ding. I don't know. Just a bell. I can bring some tuning fork and do that. Okay. Right. And the speed of sound in air, right, is 334 meters per second. If you don't remember that, that's way back when we did waves, right, sound waves. Right. We can actually calculate the wavelength of that sound, right? So it's about a third of a meter. Okay. So the wavelength is about this long. Okay. Okay. If we plug that into this condition equation that we have up here, right, 33.4, right, basically DC is the square root of 2 times the wavelength times the distance, right? We end up with a DC of the critical width of the slit opening of about 0.8 meters instead. So basically the width of that door, right? Okay. And the reason that, okay, so like if I was treating my sound wave as a ray, right? So only the people right in front of that door, into that wall can hear me, right? But since the width of this door, right, is around 0.8 meters, or actually less, right, we actually have to treat it as a wave, and therefore if you treat it as a wave, it'll actually diffract and have this opening angle, right? So what happened is that, let's say someone is talking in one room, right, is creating waves that hits a opening, okay? Person A normally, right, if we treat it as a ray, right, only a person that's right here can hear them, but due to the interference pattern and also the diffractive nature of this opening, right, even a person kind of lining up against the wall can still hear them, right? And this is why you can actually hear people around corners, right? Because the wavelength of sound is actually so long that you actually have to have a very wide opening for it not to diffract, okay? All right, does that make sense? So this is more easier to understand than light, which is, these millimeter, micrometer stuff, right? Okay. All right. Any questions about how to treat ray versus wave? About ray versus wave, right? When we're dealing with light. Okay. We're going to wrap up this chapter talking about the interferometer, which is one of the most interesting instruments. So me, as more of an experimental person, likes these things. So we're actually going to have a worksheet on it too. Okay. We're going to mainly deal with this thing called Michelson interferometer. Okay. So instead of having a 2 slits or 3 slits or 5 slits or something like that, right, we're going to create interference, right, using mirrors and beam splitter instead. How do I get this thing to go away? Go away. Right. I don't want to move it. How do I put it? Okay. All right, we're going to have this stupid cross right in the middle, unfortunately, because of the computer. Okay. So the way you build a Michelson interferometer is that you have some sort of light source. Usually this is going to be a laser. Okay. And you send all that light into a half silver mirror, meaning there's a chance that half the light will bounces get bounced off to mirror number 1, there's a 50% chance for it to just pass through. So it's like a half silver mirror. Okay, right? So the light that gets reflected off the beam splitter bounce off the another mirror, so it comes back. So there's going to be 2 lengths of travel time here, right? And then you can actually monitor whether or not you see an interference pattern here or not, right? And the interference comes from the fact that you're going to have 2 different beams coming back, right? That may have traveled different distances, right? Because you can set mirror number 2 wherever you want. You can set mirror number 1 wherever you want. They may have traveled different distances, and then they're going to combine back here, right? And depending on how the difference in the distance that these 2 path of the beams, I know I'm saying beams for waves, right? These beam waves, right, passes through, right? You will either get constructive or destructive interference, right? So once again, right, we're interested in this number delta R, right, where if it's an integer multiple of the wavelengths, then you get constructive, right? If it's half integer multiple of a wavelength, right, then you get destructive, right? So this is always going to be the case, okay? So let's see how the mathematic works out in this case, okay? We can go down here, okay? Okay. So if we want to calculate this delta R here, right? So path number 1, right? Let's say we define the distance from the beam splitter to mirror number 1 as L1, right? On this path, it's going to travel up and then back down, right? So it's actually 2 times L1 that the light's going to travel, okay? Right? On this path, if we define this length to be L2, right? This beam is going to have to travel 2 times L2, right? So the difference between them is going to be, basically 2 times L2 minus 2 times L1, right? That's the difference, okay? Like over here, it doesn't matter, right? They both travel the same distance, right? So we don't need to calculate that, okay? So that means if we solve this, right, for, well, for delta R, sorry, for L1 and L2, we impose this condition that delta R has to be m times lambda, right? And delta R is actually 2L2 minus 2L1, right, divided by m over lambda, right? You divide both sides by 2. Therefore, L2 minus L1 is going to be m lambda over 2, which is exactly what this equation is, right? Okay. Imposing the destructive interference on this, right? You just have to change the m to m plus 1/2, right? Okay. Right. So you will get constructive interference if the length difference between the 2 paths, right, is just some integer, right, multiplied by the wavelength divided by 2, right? Or you get destructive if it's a half integer version of that. Okay. And this forms a little pattern like this. I don't know how clear that is with red, with this bright light here, right? So the reason it's circular, right, is because, right, what happens is that as the light passes through, right, there's different delta R's that happens, right, depending on where you are. Okay? Okay. So this is the pattern you will see if you, well, we actually have a setup over there. You can actually see it yourself if you have time. Okay? So one of the things you want to do with here, right, let's say, right, we can actually move mirror number 2 a little bit closer or a little bit further away, right? So when you do this, what happens is that you basically could make a particular situation where you're changing this L2, right? So you can make something that's used to be constructive to make it destructive, and then constructive, destructive, constructive as you move mirror number 2 around. Okay, right? I think this will be more clear with a little example quick instead of me jabbering about what it actually does. So let's just do this example, okay? Where we're going to use a microsecond interferometer to measure the wavelength of light, okay? So in the experiment, actually it's exactly what we do in the lab over there, where we have some neon laser, right? Okay? And we want to determine the wavelength of the neon laser somehow, okay? So what the experimenter did is she slowly moved mirror number 2 until there was a 10,000 new bright central spot that appeared, meaning, right, as she moved the mirror, the spot keeps appearing. It's basically what's known as a fringe shift, right, where you change from a dark fringe to a bright fringe, a dark fringe to a bright fringe. Basically, if you look at the middle here, yeah, go back up, right? This is like blinking on and off, 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 okay? And that stuff you can count very easily, right? In fact, you probably count it with a computer instead of a human person counting up to 10,000, which will take a while, right? So when she got 10,000, blinking of that central spot, what happened is that she measured that the mirror actually moved about 3 millimeters, okay? So the setup for this is that, well, we're going to have the number of fringes, and the way we're going to quantify that is we're going to call that delta m. Remember, m is basically an integer that we iterate, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We have a delta m of 10,000. This is 10,000 fringe shifts, okay? We can call these fringe shifts, right? But in actual measurement in the lab, it's basically the blinking of the spot in the middle, okay? Okay. Right? And she found out that she translated the mirror, which moves out, basically length number 2, 3.164 times 10 to the negative 3 meters, right? Okay, I want to figure out the wavelength of the light, okay? So we can use either equation, either the constructive or the destructive one, right? Where it's basically L2 minus L1, right? Going to give you m times the wavelength divided by 2, okay? Right? So we started off, right? Let's still set up. So if we want to solve this, we want to figure out the change, relate the change in L2 to change in m, right? So let's say initially, right, we define that as just L2 minus L1 plus, some m number that we don't care about, right? Final, what happened is that we're going to have L2 plus, right, delta L2, right? That's going to equal, minus L1. Let's just finish up this equation, right? Where I replace this distance with that, right? That's still minus L1, right? Instead of m, we're going to have m delta m times lambda over 2 minus, is that it? Yeah, I think that's it, right? Okay, subtract these two equations. Oh yeah, subtract these two equations. M minus lambda over 2, okay? Right, that's what happens when we translated mirror number 2 by some distance delta L, okay? If we subtract these two equations here, right, basically the L's subtract with each other, L1, L2 both subtract with each other, m lambda over 2 also subtract with each other, right? And the equality here will be just delta L2 equals to delta m lambda over 2, okay? You can solve this whichever way you want. You can do a substitution if you want, but I think subtracting the two equations is nice, right? And therefore, right, if we want to solve for the wavelength, right, this is what we want. We know what delta m is. We know what delta L is, right? So we solve this equation for lambda. Lambda is just going to be delta L2 times 2 divided by delta m, right? And delta L2 was 3.164 times 10 to the negative 3. We have to multiply that by 2. This will be in meters, okay? And delta m was 10,000, right? Okay. In fact, I can probably do this. Maybe I can do this. Might be able to do this in my head. Divide by 2. Oops, multiply by 2, not divide by 2. Okay. So the answer here is actually going to be 630. It's going to be 4 sig figs, 2.8 times 10 to the negative 9 meters. Okay, right, which is a which is basically a red light. Okay, a pretty dark red light. Okay, so that's how you use the microinterferometer to calculate things. You're always looking for change in fringe shifts versus the change in the length. Okay. All right. Before we can go into the worksheet today, unfortunately, this problem came from chapter 33, but the book didn't actually give you exactly the information to actually solve it, because we actually, before you can solve this problem on the worksheet, we actually have to talk about the refractive index. Okay. The refractive index tells you how fast light travels in a particular medium. Okay. So in vacuum, the speed of light is always going to be 2.99792.458 times 10 to the 8 meters per second. But if it enters either air, go up here, air, it'll go a little bit slower by 1%. Okay. If it enters water, it's even slower. It loses 25% of its speed. If it enters glass, it's actually lose 33. If it's diamond, which is actually stuff with one of the highest refractive index, it's actually lose half the speed. Okay, so what you see here is that, well, if you were going slower, right, but you're gonna have to go at the same frequency still. Okay, what happens is that as you enter the medium, right, all of these wavelengths has to fit in the same has to fit into a shorter and shorter distance, because the light always travel the same distance, a different distance with the same amount of time. Okay, so the concept you want to remember is that, well, when light travels through a medium, the wavelengths kind of get squished together. Okay, especially in diamond, where you're basically going to cut the wavelengths by half. Okay, okay, so the definition for refractive index is actually if you have the speed of light in some medium, it's actually whatever the speed of light in vacuum is divided by that refractive index. Okay, so if the refractive index is 2, then you go, the speed of light in that particular medium is half the speed of light. Okay, right. I'm going to go through a couple of derivation here where, right, if you want to convert that information into wavelength, okay, the wavelength is actually going to be also cut by whatever the refractive index is. Okay, so let's say, in vacuum you have some light that is actually traveling has a wavelength of 500 nanometers, but let's say it enters diamond, right, which has an index of refraction of 2. Okay, it's actually going to be 500 nanometers divided by 2, in other words 250 nanometers. Okay, right? When the light enters a particular medium, it shortens the wavelength, okay, by the factor of whatever the refractive index is. Okay, okay, okay. This is going to be concerned on this little worksheet here, because what the worksheet asks you to do, which is a problem in this chapter, even though they didn't talk about refractive index in this chapter, is they're going to, instead of translating mirror number 2, right, moving it so you actually have a delta L2, what they ask you to do is actually put in a little air cell in here with a length D, okay, right? And this little air cell is going to start off at a vacuum, right? So vacuum, the index of refraction of vacuum is exactly 1, okay? But then you're going to slowly let air into here, okay? And so it changes the refractive index inside that cell from 1 to 1.0028, which is the refractive index of air. Okay, and you can actually, what happened is that, well, then you actually will start, instead of changing the length here, you effectively change the number of wavelengths of light that will fit in this air cell. So you're going to have this fringe shift where you have this bright spot, dark spot, bright spot, dark spot, right, that you can count also. Okay, so that's what we're going to do on the worksheet today. With 10 minutes, which is not enough time.